Okay, dear participants, now we have a small discussion for the project theory of definability, logic, algebra, and geometry. So Alexey Lvovich, our speaker, will start now.
So today is the final presentation of our project on definability theory. And as you remember, it's a combination of consideration in logic, which is the origin of our problems, but also we apply some considerations from geometry and algebra. And it's some conference of the determinant of towns. So I'll start with an example of what is definability. And this is an example is one of the problems for our participants to solve. So the problem was how to define in what's called arithmetics, means system structure of natural numbers with relations of addition and multiplication, and how to define a power of 6. The previous problems were easy enough. It was a problem how to define powers of 2, powers of 3, then powers of 4, which is a little bit more complicated, but of course it's just a square of power of 2. But when the participants started to consider power of 6, it happened to be much more cumbersome. And there's a straightforward way to solve it, the problem, which is to find a way how to define arbitrary long sequences via a property relation with only a fixed final number of arguments. There's a famous Gödel proof of his incompleteness theorem, where it was used so-called beta function of Gödel with 3 arguments. 2 were to fix a sequence, and the third one was a number of elements in the series, in the sequence. And some of our participants really discovered something similar to this Gödel coding for sequences. But one of the participants found a very short solution. Could say simple, but actually it's not so simple because others didn't found this, and even the authors of the problem didn't expect that kind of solution. So look to the screen, please. So let 6 in power of k equals to 2 in a and 3 in b. We would like to describe in arithmetics what does it mean that a equals to b. It's easy, of course, to find 2 in a and 3 in b through 6 and k. Naturally, there's the maximal exponents of 2, powers of 2, and powers of 3 that divide 6. Okay, that's clear. Of course, I will not I'm not going to write formal formulas in arithmetics. I hope if you listen to this and see the screen, you can easily reconstruct formulas. So the trick which Valery proposed was to find a big prime number, any big number, any big prime, just greater than 6 in k. And then simple congruences, p in them plus 2 in a equals to 0 modulo p plus 2. And similar for 3. And because really p is a very big number, then you just have that the minimal solution for this will be in the case where a equals to m and n equals to b. And so we have for this P the solution for the problem. This works when A and B are even, are odd. If A and B are even, you have the very simple trick to have the whole solution. So I hope you can easily repeat this, having the very idea of this prime number P. So the next what we're going to discuss is that we actually use some general scheme for our solutions of definability problem. Definability problem itself is describing the definability lattice of a given structure, and the lattice consists of all the what we call definability spaces. All the relations definable through some set of relations. In our case, one relation. Yes, if you have any finite number of relations, it's actually the same and to have one relation. For infinite of it is different. So we divided the solution of the problem in 4 stages. First is just to look to a given structure. In our case, it was a numerical structure with a basic set universe, a set of numbers. Practically, there were rationals and integers. And the original relation defined on this was less an order relation for rationals and successor or +1 relation for integers. So starting with this one relation, you can define other relations. Just we start with relation in between for rational with order. So you construct more and more relations, then find that, yes, perhaps you found the whole set of non-equivalent relations. Relations are equivalent if they're mutually definable. You can define one relation to another one and vice versa. Okay, then you're going to the next stage. In this case, you use the idea of geometry. For a geometry is very powerful, and it was there, remember, the Klein Erlangen program where you use transformation groups which keep invariant this or that relation. And so for each of our relation we discovered, we construct a group of transformations. Okay, so we have such and such relations. There you have this and this transformation groups for them. If you have transformations groups equal, then the relations are perhaps equivalent. Actually, it's not completely true. There is a so-called Svinonius theorem, we mentioned this, which gives a trick how to have this statement really correct, that the equality of groups of transformation is the same as the equivalence of two relations. But in our cases, we really have this kind of equivalence. Okay, so if we have different groups of transformations, then it's pretty evident, and I believe it's evident for everybody who listens to my presentation here, that the relations are really different. You cannot define one relation to another and vice versa if the groups of transformations are the same. That's the second stage. The third stage is the most complicated one. This is to prove that there is no other relation or no other group of transformation in such and such structure. So this is a very, sometimes it's very non-trivial, and in most cases it's easier to consider groups because a lot of technologies developed with groups, and it's harder to consider just formulas by themselves. Nevertheless, in some cases you need to consider formulas as well. So the last step Actually, it's more like routine and technical one. And this is really to describe the whole lattice of definability. Means for any two pair of relations, or classes of relations definable through this or that one. Find the supremum or infimum. And that's we have the whole structure. Okay, so what was discovered by the participants of the project, members of the project, for the order of rationals? Naturally, we start with x less than y. Then we discovered what I mentioned in between, b, means that y is between x and z. And here we can see this disjunction of two options. Then you'll have cycle, and it have very clear graphical representation. If you just really make a cycle out of rational numbers, then you have one more relation, which we called S with 4 arguments, and means that two open intervals, xy and zu, intersect, but not one lies into another. So, and the minimal relation, which we assume is in any class of relations, is just equality. Okay, so on the second, that's what the first stage was discovered by, yes, not by all, but many of the participants. So the second stage is to construct the transformation groups. If you let's start with just order relation. For the order relation, it was discussed even in my first presentation for the project. The group consists of all increasing continuous transformations. You can easily imagine how or just will be good if you draw it on a sheet of paper. What means relation? What means be increasing continuous transformation of rational numbers? Just remember that the transformation is in other cases in geometry. You just have one-to-one correspondence of the set and its mapping onto itself. So you have this picture now. Okay, all the groups we consider later consist of these transformations. What do you think? How many of the transformation exists? Natural numbers is an countable set, but the set of all these continuous transformations, you can think about this. Okay, so then for between relation, we have all these transformations, of course, but also all continuous decreasing transformations. So if we have, for example, a minus of a previous gamma set, you'll have this gamma B. Gamma C contains what can be called transpositions, means that the graph of this looks like a shift of the hyperbola, where for two irrational numbers, parameters S and T, you have the maps with consists of two intervals. On each of them, the graph goes increasing. Then we have gamma S, and gamma S is generated just by all transformations from groups gamma B and gamma C. Again, the group for the equality consists of all transformations. So you can interchange any rational number for any other rational numbers. Of course, identity is preserved by any of these transformations. If you look to this sequence, you will see that gamma is a minimal set of transformation. And the class of relations defined with gamma is maximal. Actually, it's a universal property. So we have a correspondence between a set of between classes of relations and corresponding groups, and this is what is called Galois correspondence. And in this case, it reverts an order. So we have two lattices, and one lattice is in Galois correspondence to another lattice, but the order relation in this lattices is reversed. Okay, so next stage is the very complicated one, and I will not give you detailed proof, but just to mention that some of the members of our team, of our project, really constructed this. Not to very, very specific detail, and something should be checked again, but in general principle was followed by, and the most of the whole proof was constructed. So the idea of the proof is to consider the notion of K-transitivity. So a group G is called K-transitive if for every two couples, as you see, A1 AK and B1 BK, where all the members of each family is different, we can transform first sequence to second sequence. For example, the very group gamma for all consisting of all monotonous continuous transformations, of course, can translate any rational point to any other rational point. It's evident. But it's not too transitive, just because if you take A1 less than A2 and B1 greater than BK, it's impossible, of course, monotonously translate this couple to the first couple to the second couple. Okay, but if you take gamma B, it is too transitive, so we can transform any two rational numbers into any three rational numbers. But it's not three transitive, just because if the number is between two others, it still is between two others. So we cannot just put it outside. Then we'll see that the important issue is that if you have these transitive groups, then you can consider orbits for couples, for three triples and etc. relations, and having transitivity, you can out of being non-transitive, we can have orbits of these couples, etc. And for any of these orbits, you can construct a formula. So in fact, the process is like you have a transformation group, then you have orbits for some tuples of elements of rational numbers. And then out of these orbits, you construct relations. And the construction is happening just by stages. You construct something for two transitive, not three transitive, etc. And the most important point here is that if you comes to a stage of, say, 5 transitive, you'll discover that there is no 5 transitive groups, which is not, say, infinitely transitive. The natural notion of transitivity is that for any number of members in the vector, you can translate it to any other vector of the same dimension. So, and let's finalize the proof here. And some of the, as I mentioned, some of the participants really came to some full understanding of the situation. Okay, so the fourth stage is easier here, and it's just a full construction of the lattice. So you can just look, it's just definition of what is exactly the lattice, what is supremum, what is infimum, infimum and supremum for the members of the lattice. And you can just stop the video and if you need to write the details of the definitions here. So, and here the lattice. There are some additional technical marks here, but you can clearly see what's happening actually. So the maximal set in the definability among the definability spaces is just Q with order. Then you have 2 members of the lattice just below it, and there's nothing in between. First is cycle, second is between. And then you have the intersection, the infimum of cycle and between, which is separation, or in our case, we call it separation S or link. And then you have this Q. So you can see this kind of nice picture that really we have 5 members of the lattice, as you can see here. So the second case was integers with successor. And the first stage, we discovered not a finite number of sets of relations, but a finite number of series of these sets with a natural parameter n, as you can see. So the first one is y equals x plus n. You remember the successor is just plus 1. So the among this an, there is this y equals x plus 1, and that's the maximal set of relations we consider here. So the second case, as you see, is that, let's start with the Cn, with the third case. Cn means that distance between x and y equals to n. Okay. And the second case is that the same x and y, the distance between x and y is n, and distance between z and u is also n, and xy and zu are oriented to the same direction. So if you see y is greater than x, then u is greater than z. So this is the series, and not immediately, but in some time, some of the participants discovered these three series, infinite series. And then the stage 2, how to find sets of transformations. And again, pretty fast, these transformations were discovered. For example, of course, there is a shift. You can add any natural number to all the members of Z, the same number, and it will keep invariant the original relation successor. But what is nice and interesting, actually, if you have the relation as you can see here, an, for example, and in fact bn and bc and cn, then you can shift one arithmetic progression to one distance and another arithmetic progression to another distance. That's an interesting situation, and it's exhibited here. Also, for some of the transformations, the reverse or of the naturals also works. For example, if only distance, like in CN, is interesting for us, then of course you can use also the which can be called transposition. You can reflect the integers over zero, for example. Okay, so the whole set of groups can be defined by this, and we can happily discover that such and such groups can correspond to such and such sets of relations, A, B, and C series. But it's pretty sophisticated to prove that there is no other group. And so what really happened is some of the participants came pretty close to the proof, but nobody really was completely successful in finding the proof for no other transformation. And now, yes, so that's it about the second case, which we considered in our project. And now just we try to construct together with other participants the set of open problems or problems which were unsolved in our project. Again, looking for the numerical sets of numbers, you can have Q, Z, and N naturals. And consider relations. One is just less, and for Q we solved in our problem. For Q and plus one, you can try to look what happens if you have just x plus one with Q, and for x plus y additional relation for Q, it's actually we work with this, and hopefully we can have good results eventually. One thing which I did not mention on the previous slide, it's just my mistake, and when considering Q x plus one, I just recollected this. In fact, what was important is that for just one case, we cannot prove that two relations are different, two classes of relations are different, but it looks very different, and it's actually B1 and C1. But we cannot prove this because we don't have enough groups. And in this case, actually, what was proposed and was done by the participants of the project, members of the project, is to have another copy of integers of Z, and to have group acting both on the original Z copy and on the second one. And in this case, we can find additional group transformation group and prove what we needed. So but also we can use countably many copies of integers, and actually it happens when you work with Q and x plus one. Yes, so we have we have some results on Z and x plus one inside our tournament, but it was completely solved by us and published this year. Just to mention that the problem for Q and less, it was published in the year 1966. So, and for N and x plus one, we have some results of some of the participants, and perhaps it's very close to final solution for this, and the solution is based on the solution for Z. So finally, the plus. For the plus, Q is, as I mentioned, is in progress. We are working on this, but for Z and N, it will be pretty hard. It will need some additional techniques to prove this as we feel. And we propose a couple of more problems, and there are actually very many problems of that type for definability theory. One is that branching integers, like integers, but the relation is just to be neighboring, but any element, any vertex of this graph has just 3 neighbors. And another problem is order of non-negative rationals. Actually, to what I'm going to say at the end of my talk is that the field of definability looks very natural. And it was considered from the very beginning of this the setting of mathematical logic, even in 19th century, by great names such as Peano or Hilbert and Alfred Tarski. But it was not so much investigated for many decades now. And so we propose for more young mathematicians to work on this field and perhaps present their results to us, and we try to help to popularize this result and to publish it in the leading mathematical journals in different countries, in Russia, in England, and France, where some groups of researchers work on this problematic of definability theory. So just we appreciate the participation of online and of course something who will be together with us in Kostroma region of Russia, working on all these problems. So thank you very much for your attention. Goodbye. Все.
Thank you very much for the discussion. It was very interesting. Thank you.
Goodbye.